So, thank you, Victor. I'm very happy and very proud to be able to speak at this conference in honor of Roger and Sylvia. Thank you for inviting me to give a series of talks. One of the reasons I'm so proud to speak here is to convey how much I've learned from Roger and Sylvia. Not only mathematics, though almost everything I'm going to talk about I learned from Roger, but also how to be a mathematician, how to be a professional, how to be a friend, how to be a rock climber. To be able to give a little back is a great pleasure for me. So thank you for the opportunity. So, as Victor said, how's that for size? Is it too small, too big? It's okay? It's okay. I'm going to discuss some results in direct sum decompositions of modules over local rings. So just as a 30-second overview of the entire 3-lecture series, the situation is this. There is a best world, which is described by the Krull-Schmidt theorem, where everything is beautiful. And we can identify this world, and then we can ask, how bad is the rest of it? And the answer is actually very interesting. It's not as bad as you might think, but it's pretty interestingly bad. So we'll discuss how bad direct sum decompositions can be, and find some very interesting phenomena. So, part 1 today is about the Krull-Rimac-Schmidt property, and hopefully, depending on how much time I have, I'll get to discuss semigroups of modules. So let's begin. So throughout, I'm going to work with a commutative ring, R, a commutative and Noetherian, which for the moment is just a ring. In a little while it will become a local ring, but not right now. And we'll discuss only today, only finitely generated modules. The other main player in all of this is the endomorphism ring of this module. So this is R linear maps from M to itself, which is a ring, of course, under composition of these maps. It's probably a non-commutative ring, even though we started with a commutative ring to begin with. So let's say that M is decomposable if it can be written as a direct sum of two other modules, both of them non-zero. Otherwise, of course, it's called indecomposable. And second, maybe I'll sneak it in down here. An endomorphism, let's say call it E, in this big E, this endomorphism ring, is idempotent if E squared is equal to E. Now, of course, these things are related. This is why I make them part one, part two of the same definition. Specifically, if 0 and 1, that is, the identity map on M, are the only idempotents of E of this endomorphism ring, then M is indecomposable. If there were a decomposition, then the projection onto one of the summands and then inclusion back in would be an idempotent, and vice versa. The same argument, standing on your head, proves the converse. This is very soft chalk. So because we started out with a finitely generated module, and because we started out with an Noetherian ring, we can always decompose this module M into a direct sum of indecomposables. Say M1 up to Mn. And this, as I mentioned, is because we're working with finitely generated modules over a Noetherian ring. However, such a decomposition is generally not unique. So we come finally to the Kroll-Schmidt property, which is a property of the ring to the effect that all of these decompositions are unique. So let's say R satisfies the Kroll-Rimac-Schmidt property. Which I'll abbreviate as just KRS. If, whenever you have two direct sum decompositions of the same module, into indecomposables, there are the same number of summands, and you can match them up. So M is equal to N, and Mi is isomorphic to Ni, maybe after permuting the summands. So the first example that we see of a property like this is in the fundamental theorem of finitely generated abelian groups. You can take any finitely generated abelian group and write it as a direct sum of a free abelian group with some torsion, and it is unique under some assumptions on the torsion. But it's not at all hard to write down examples where the Kroll-Schmidt property fails. So I want to write down actually two, just to give a hint of what can go wrong. So let's take an example. Let's look at the polynomial ring in two variables over the rational numbers. And let's set M1 to be the ideal generated by the variables, x and y, while M2 is the ideal generated by x minus 1 and y. So these are two maximal ideals. Oh, by the way, I noticed that the schedule for most of the talks, they're supposed to be 40-minute talks with a 5-minute question period. But my talks are 45-minute with no question period. So if you have questions, you should interrupt in the middle. Okay? If something seems weird or wrong or just confusing, please stop me. Okay, so these are two maximal ideals of the ring, and we notice that the sum is the whole ring. So we can write down a short exact sequence. This is a slightly fancy way to say this, but there are less fancy ways. This one's just faster. We get a short exact sequence from the direct sum of these two maximal ideals onto the ring which sends, let's say, Fg to F plus G. And that's surjective because of this. And the kernel is nothing but the intersection. And because the right-hand end is the ring, this splits. There's a splitting back to the middle, and so the middle is isomorphic to the direct sum of the two on the outside. And I won't fill in the details, but I'll just say one can check, and I'll even say easily, that neither of these maximal ideals is free of rank 1 as an R module. So this, what is this? This is that, is a failure of Kroll-Remak-Schmidt property. Great. The cardinality is still stable. That's true. There are still two summands on this side and two summands on this side. That's true. Now, if you recall, my title said something about local rings. And it's pretty clear that this example arises from the fact that there are two distinct maximal ideals. So maybe you think that if you rule out such behavior, if you rule out having more than one maximal ideal, everything's fine. That's not the case. So let me show you a quick example that Kroll-Schmidt can fail over local rings as well. And this is due to Richard Swan as written down in a paper of Graham Evans. Some medium-sized number of years ago. So it has to be a little more complicated, so here's how it is. Let's take R to be the rational numbers adjoin now three variables, x, y, z, modulo one equation, so y squared minus x cubed plus x squared. And then let's localize this at the maximal ideal x, y, z. So geometrically, this equation in two variables defines some kind of cusp. Because we've thrown in a third variable, it's some cylinder. Node. I'm sorry, I wrote the right thing and said the wrong thing. It's a node, and it defines some kind of cylinder. Boy, that's terrible. Anyway, it's a cylinder over a node. So this is a local ring because we forced it to be one, and is a two-dimensional domain, integral domain. And why is it domain? It's because you can't take a square root of this part in polynomials. If you were allowed to use power series, you could, and that will be relevant later. But I'll point it out when it comes. So it's an integral domain. So let's set R to be, or excuse me, A to be R adjoined y over x. So this is the smallest subring of the quotient field Q of R, containing R and this fraction. And we notice y over x, when you square it, you get, well, of course, you get y squared over x squared. But in this ring, y squared is equal to x cubed minus x squared. And now these we can divide. This is just x minus 1. And one can see, this is, I'm going to leave out the details here. We can see that A has two maximal ideals. Let's call them big M1, generated by, make sure I get it right, X and Y and Z, and this element minus 1, and then also X and Y and Z, and that element plus 1. No. No, I don't want to localize. It's got these two maximal ideals. So, no, what I want to do is I want to force it to be not local, because I want to mimic this over A and then descend to R. You're about 3 lines ahead. This is treacherous. So, as I hinted, we can use the same trick as in the previous example to see that we have a failure of Krull-Schmidt over A. Just as in the previous example. And hence, as R modules. And the last step is to see that if A were isomorphic to one of the MIs as R modules, then it would be so as A modules as well. Because A sits in between R and its quotient field. So any homomorphism giving this isomorphism, you could clear denominators. Any R linear map is automatically A linear. by clearing denominators. So what we've done here is, over this local ring, constructed a failure of Krull-Schmidt as well. Yes. The Z is not really doing anything. It's kind of hiding in here, actually. To make it easiest to show this, you want it to be not a one-dimensional ring. So what Graham Evans does is he says, what does he say? Oh, he says it's a maximal ideal of A. Therefore, since A is two-dimensional, it needs at least two generators. So you can't have this as A modules. So there are other ways to do it, but I just wanted to follow Evans' argument. Okay. So we've seen now that Krull-Schmidt, while nice, is not universal. Next, I want to identify the key property that gives us the Krull-Schmidt. Property. So let's make a definition. And for this, I need to become a little bit non-commutative. Not very, just a little bit. So let's let lambda be a ring with Jacobson radical that is the intersection of all the maximal left ideals or all the maximal right ideals. Let's call it J of lambda. And let's say that, oh, here, put it here. Let's say lambda is NC local. NC stands for not commutative. If the quotient of lambda by its Jacobson radical is a division ring. So if lambda were commutative, this would say lambda mod its Jacobson radical is a commutative division ring, that is a field, and therefore this is a maximal ideal. It's the only maximal ideal. So this is an appropriate generalization for non-commutative rings. Equivalently, the Jacobson radical consists exactly of the non-units. Of lambda. And then part two of the definition, let's go back to the commutative world. And M, a finally generated R module. And let's say that M is what I'm going to call strongly indecomposable. Strongly indecomposable if its endomorphism ring, which we discussed earlier, is one of these NC local rings. So the first thing to observe is that if lambda is an NC local ring, then it can't have any idempotents other than 0 and 1. And this is because if E squared is E, then E times E minus, whoops, well, either way, E minus 1 is 0, so E is a non-unit. So it's in the Jacobson radical. Same goes for the other one, E minus 1. So the Jacobson radical is the whole ring. That's just a very quick sketch. See if you can find where I used that E was not 0 or 1. So that says that this strong indecomposability implies indecomposability, as the language requires. Now, a quick lemma, which I won't prove, but am I allowed to assign exercises? I think so. I'll assign this as an exercise. So let's take a strongly indecomposable module. And let's just take X and Y, arbitrary finitely generated modules. So first, if M is isomorphic to a direct summand of the direct sum, X plus Y, that's far too long a phrase to write out every time, so let me write it as M divides X plus Y. Then either M divides X, that is isomorphic to a direct sum of X, or M divides Y. That's part 1, or part A, and part B. If you have an isomorphism M direct sum X isomorphic to M direct sum Y, then you can cancel the M's. So we think of this, can I write way over here? Sure. This is saying that M is prime-like. It satisfies a condition like being a prime integer. And this one is some cancellation property. So, in this sense, strongly indecomposable modules are like prime integers. In these senses. And this is enough, or these properties are enough for the Kroll-Riemann property to hold. So let me write that down. So let's take some modules M1 to Mn. Let's assume these are indecomposable. And then also some modules N1 to Nm. Let's have those be strongly indecomposable. Then the statement is if we have an isomorphism between the direct sums, then there are the same number, and you can reorder the n's or the m's. So that the indecomposables are isomorphic. And this is really immediate from the lemma. This is very formal, just using cancellation and the fact that they are prime-like. So this is pretty good. So if our modules are strongly indecomposable, Kroll-Schmidt holds. And we know that strongly indecomposable implies indecomposable, so now the real question is the converse always true? Well, of course we know it's not, because we know examples. But when does the converse hold? That is, when does indecomposable imply strongly indecomposable? This, if we can give a complete answer to this question, we'll have a complete answer to which rings have the Kroll-Schmidt property. None of those guys were strongly indecomposable. Well, I guess the free module of rank 1 is strongly indecomposable always, but none of the rest were. Oh, maybe the intersection is. I'd have to think about it. All right. In the last few minutes, I want to approach an answer to this question. I think I might be able to get all the way to the answer. So let's define a local ring R to be Henselian if it satisfies one of the following properties, which are actually equivalent to each other. First, for a monic polynomial, oh, I guess I should give it it's a local ring, so let's give its maximal ideal a name. And K is the residue field. So for a monic polynomial with coefficients in R and a factorization, F bar in K bracket X. So that means when you kill the maximal ideal, F factors into relatively prime factors. For any such F and any such factorization like that, there is a factorization that lifts the given one. In other words, when you go modulo the maximal ideal, G becomes G naught and H becomes H naught. So that's the first. The other two are a little quicker. Or do I have two or just one? No, two. Every commutative module finite R algebra. So this means it's an R algebra that's finitely generated as a R module is a product of local rings. And third, for every module finite R algebra, say lambda, not necessarily commutative, you can tell because I called it lambda. Idempotence of lambda mod the Jacobson radical lift to idempotence of lambda. So the fact that these are equivalent is not obvious, and there are 3 or 4 more equivalent characterizations of Henselian rings, but these are the 3 that are closest to what I've been talking about. And if you have taken a class in number theory, you might have seen something like this. It's called Hensel's lemma. It says that complete local rings satisfy property 1. But the relevance of this property for me today is that Henselian local rings are almost precisely the ones for which the Kroll-Schmidt property holds. So let me finish with the following fact, which again is due to Graham-Evans, well, at least half of it is. Half is sort of folklore. If R is a Henselian local ring, then every indecomposable module finally generated as always is strongly indecomposable. So R satisfies the Kroll-Schmidt property. That's the first half. And the second half, which is really the part that Graham-Evans did, is that the converse is almost true, which is that R is Henselian if and only if R, not only R, but also every module finite R algebra satisfy the Kroll-Schmidt property. So I started a few minutes early, so I'm going to also quit a few minutes early. My plan for the second lecture is to talk about semigroups of modules, which I didn't quite get to today, and try to get a better handle on when Kroll-Schmidt fails, how badly can it fail. So thank you for your attention.